This is Dr. Holt. This video is on linear momentum. When Newton devised his second law, he considered the product of mass and velocity as a measure of the object's quantity of motion. Today, we call the product of the particle's mass and velocity linear momentum, and is denoted by the symbol P. The quantity is called linear momentum of a particle to distinguish it from linear momentum of linear momentum from angular momentum, which we'll get into in future videos. Linear momentum now is a vector quantity and is noted by the vector symbol here. Again, it's a product of just velocity and the scalar mass. The magnitude mv is in the same direction as the velocity, and the units of measure of momentum will be in kilograms times meters per second. Momentum may be thought of as a measure of the effort needed to bring a particle to rest. For example, a massive truck has more momentum than a small passenger car traveling at the same speed, and it takes a greater force to stop the truck in a given time than it does to stop the car in the same amount of time. When the sum of all the external forces acting on a system of particles remains zero, then the rate of the change of the total momentum remains zero. In other words, the summation of all the masses and velocities initially will be equal to the summation of all the masses and velocities in the final, and this is called the law of the conservation of momentum. The strategy I'm going to recommend when it comes to problem solving is to usually draw a sketch showing the system before and then show it after the time interval. I would include coordinate axes, and I would label the initial and final velocity vectors. Then equate the initial momentum to find the final momentum. So you can say that m1 times v1 initial plus m2 times v2 initial, etc., will equal to v1 final velocity final plus m2 final velocity. Now once you have that, then we'll be able to substitute back in to find the unknown. And I'm going to work a couple problems here. The first problem, let me go back and get a regular pen. The first problem is I have a runaway. It's a 14 kilogram railroad car. It's rolling horizontally at 4 meters per second toward a switchboard. As it passes by a grain elevator, 2,000 kilograms of grain suddenly drops into the car. How long does it take the car to cover the 50 meters distance from the elevator to the switchyard? Assume the grain falls straight down and that slowing due to rolling friction or air drag is negligible. So again, we'll draw a kind of a picture of what's taking place here. So initially, I have a car. We'll just draw it with a rectangle here. And again, I would draw my velocity like this. And my initial velocity is going to be 4 meters per second. This is my car, and the mass is going to equal to 14,000 kilograms. So P, initial, go with a vector symbol, will equal to the mass, which is going to be 14,000, times the velocity, which is going to be 4. And that's going to give me a value of 56,000. And that will be in kilograms times meters per second. And again, I'll go ahead and just show this as a vector too. This will be my velocity. Okay, and this will be a vector quantity here. Alright. So now what we can do is we know our final has to be the same. So we'll draw another picture of what's taking place final. Actually, I'll go ahead and get rid of this vector because I'm showing pi, the initial, as a vector. So what's taking place here is, I don't know my velocity. So the final we don't know. Now the mass has changed. We've had 2,000 come in, so now I'm down to 16,000. So that's going to be our mass final. So now we just write the conservation of momentum. And we know that Pi is going to equal to Pf. We know we had 56,000 initial. That must equal to 16,000 kilograms times my final velocity. Final. Again, that's going to be a vector. We'll solve for that. And when we do that, we will find that Vf will be approximately 3.5 meters per second. Okay, and then our velocity would be going to the right because it was initially going to the right. Make that vector a little bit better. Arrow go better, going this way here. Okay, so that's our final velocity. So now we have, the question asks us, how long did it take the car to cover 500 meters? Now here we have no acceleration, so basically we just have displacement. So we go back to our kinematic equation. The delta x is going to equal to vi, our velocity, times t, because we have no acceleration. So that would be our displacement was given as 500. So we put 500 is equal to v, which is 3.5 times t. We solve for t, and we'll get 143 seconds. So this problem's not bad. Again, the key right here is this, the conservation of linear momentum, which apply that. Then you can find your velocity, and then from your velocity you can find the time. All right, let's look at one more problem here. Here I have Judy mass. She has 40 kilograms standing on a slippery ice. Catches her leaping dog Tony, mass 15 kilograms, moving horizontally at 3 meters a second. What is the speed of Judy and her dog after the crash? I'll go ahead and draw a vector coming off this way. The dog is moving at 3 meters a second. The dog has 15 kilograms of mass. The girl has a mass of 40 kilograms. Okay, so this is going to be our initial condition. Okay, so now what's going to happen final? Well, let's just go ahead and move this down here. I'm going to kind of grab some of this. I'll move it down. Okay. For this. Okay, now the dog, dog and Judy were one item here. So now we can draw a vector going back this way as far as the velocity would go. Okay, now the mass here would be the dog and the girl combined. So mass final is going to be 40 plus 15, that's 55 kilograms. And now all we have to do is apply the conservation of linear momentum, because there's no forces being occurred here, no external forces. So our linear momentum initially is going to be the mass of the dog, which is 15 kilograms, times the velocity of the dog, which is 3 meters per second. That will give us 45 kilograms times meters per second. Now I have the dog going to the left, so I'll show this going off to the left. PI final. PI final. The momentum final must equal also 45 kilograms times meters per second. We set that equal to the total mass, which is now 55 kilograms, times final velocity. And all we have to do is solve for final velocity, and final velocity will get to be 0.82 meters per second. Going in the same direction, we're going off to the left because we made it off to the left, the same direction as what the dog was going. So here are two examples and a short presentation on the conservation of linear momentum. I hope this helps you understand the concepts and how to set up these problems. Best of luck.